and chat. Okay. So the syntax for Lambda, Python Lambda is pretty straightforward. Keyword Lambda, then the arguments, and then one expression. They're limited to one expression. So here I'm assigning it to, a variable called ink, and then we can call that like any other function. Multiple arguments, can just list arguments, colon, slightly more complicated example that I use a lot. So I'm defining a function adder, and it returns a lambda. And the key thing here is the lambda references the argument to adder function. So when I call adder give 5, add 5 now is a variable which holds a lambda, and the lambda knows the value of n is 5. When I call it again, right? Add 9 is again a variable holds a lambda, and the lambda's value of n is 9. So lambdas are also closures in the sense that they remember their environments. Even if the environment goes away, the environment is remembered. And it's one of those things, if you don't think about it, it makes sense. When you think about what's going on, it gets more complicated, because how is it that, how can add 5 remember the value of n when that function call is over? But the compiler just has to create the code that will copy that value of n in the lambda. Luis, you have a question?
Yeah, Professor. Yeah, this looks very clever, but how does using lambdas help program clarity?
How does it help? I have a few examples coming up, which will help answer that.
Okay.
Right, so yeah, lambdas are also closures. So more example for lambdas. I have a list, I'm going to sort that list, right? So we can have a built-in sort routine, because we don't want to have to implement over and over again. And that makes sense, right? But we may want to be able to sort the same data type different ways. For example, you have student objects, you may want to sort them by name, you may want to sort them by grade, right? Or maybe even by zip code, or send an email or mail to them. So how do we write a general purpose sort routine that can sort student objects by name, or by grade, or by zip code? All right. Somehow we need to tell the sort routine how to sort the elements. All right. And so what they do in Python is we can pass in a lambda, and the lambda returns the value that they'll use on each object to compare, right? So here, just for an example, I'm going to sort the strings based upon length. All right. So that the way they come in handy is there are times when you want a very short little function, but it doesn't really make sense to declare a separate function just for this particular purpose. Does it make sense? Any questions? It'll help when we look at yeah, we can do a shortcut. Now we look at Java, how we do Java sorting. The way it used to be done is, right, the sort method requires a comparator object to tell the sort algorithm how we want to compare the elements that we're going to sort. And there were two ways to do this. One was we implement a class that implements that comparator interface, and all it does is, the important part is this piece right there. Now, there's a way in Java we can then define this method inside the parameter list. Either way, we've either this way we've expanded how much code we have to write and read, or we have a function definition inside a parameter list, which makes it hard to read. Right, so it's just it's much easier to use a lambda with short notation, and the intent becomes clear. So the new way, I can now declare it as a lambda. So already this is much shorter, right? We can also, do it directly. The Java syntax is a little bit verbose. Does that help answer your question, Luis?
I'm really not familiar with the lambdas. I guess I'd have to get used to using them.
Yeah, a lot of students aren't. Most new languages have them built in. It took Java a long time to go that route. But in the Java world, it does simplify a number of things. Right?
Well, I've seen them in the Python documentation since a long time ago, but I never considered this something for which I would need to use them.
I use them all the time. And
maybe if we have a programming exercise to find a use for these.
You will have one soon, yes.
Good.
Any other questions? Okay. So yeah, if you're interested in Java lambdas, some documentation. Yeah. So when we talk about iterators, there's two major types. There's external and there's internal. Pre-Java 8, you only had external, so most students only knew about external, but now we've got internal iterators. When we talk about patterns, there's several things to note. One is the whole goal of the pattern movement was to find solutions to problems that people found successful in practice and be able to write them up so that other people could share that knowledge without having to rediscover it themselves. And each book on patterns tends to evolve their own sort of structure. So the Gang of Four textbook, this is the structure they have. What's the goal or the intent of the pattern, and motivating examples that understand why we might need it. When should you apply it, not apply it? What's the structure of the pattern? How are all the components relate to each other? How they work together, and some of the consequences, and the good consequences and the negative consequences. And then I'll give some, a implementation and some sample code. And so it's the same pattern that texts are going to use through all the patterns. Different texts will use sort of different structure. Usually they're fairly similar. So for the iterator, here's a structure. And again, they're not doing it for Java. They're not doing it for C++, they're not doing it for Python, they're doing it for in general. So first of all, an aggregate means some sort of collection, a list, array list in Java, or a list. Different languages call them different things. And there's some method in that collection or aggregate that will return an iterator for you. And this is an interface. And then we need some sort of concrete implementation. So in Java, the aggregate would be the collection class. And then the concrete aggregate would be an array list. And then they show you, what's going to return, some sort of concrete iterator. And the concrete iterator implements, interface, iterator interface or abstract class, and what language construct we can use. And then there's some methods. And so the client interacts with the aggregate interface and the iterator interface. So the client, meaning the code that uses the iterator, it does not know the concrete type of the iterator. It just knows the general interface. And that's on purpose because you don't want the client to know that I have an array list iterator, because the next time when you call it, get iterator or create iterator, you might get a linked list iterator, which would be different. And we don't want the client to know that, because as soon as it knows that, then we get coupled to that concrete type, and so we can no longer swap different types in or out. Right? So they always give us the pattern structure. Okay, so there's the patterns will use various names. It's like aggregate, concrete, client, concrete iterator. These are all roles that classes will play when you implement the pattern. Java does not have a class called aggregate. Does not have a class called concrete iterator. So often when students start implementing patterns, they start using names from the structure that are meant to be generic rather than specific. There are a few cases where the pattern uses names which would carry over implementation, but often it does not, right? So for example, the only name in this pattern that carries over to Java is the name iterator. The various implementation details, not the details, but issues. One is what they call a concrete iterator. So here, right, I'm creating a read string, a string reader on a string in Java that allows us to traverse all the elements of the string, right? And that's what an iterator is built to do, is be able to iterate over the elements of a collection. And a string is a collection of, in this case, Unicode characters. It's called a concrete because we know we created a specific type of iterator, a string reader. Polymorphic. So if I create an array list or any sort of collection, when I ask that collection in Java for the iterator, we do not know the concrete type of the iterator. Right? All we know is that it implements the iterator interface in Java. And the list of students is an array list. We get an array list iterator. If the list of students is actually a vector, we get a vector iterator. If it's a linked list, we get a linked list iterator. But the code that uses the iterator does not know. And it's called polymorphic because now, this code will work regardless of which type of iterator it is. I can use it in array list iterator, linked list iterator, etc. So far, so good?
So just to confirm, what you're trying to explain here is that with the right code, it could pull either from the concrete class or the built-in class. Am I understanding that correctly?
Yeah, there are different types of iterators. So the string reader is a form of iterator because it allows us to go through all the elements. But we have to explicitly ask for that type, right? We say give new string reader. Whereas here, right, we don't know the actual concrete type of iterator.
Okay, thank you.
Do we have any C++ people here? No one's willing to confess to knowing C++.
I mean, I work with it, but I don't see where the memory leak would be.
When you create an object, who should delete it?
The destructor?
Who calls the destructor?
Whatever created the object.
Ah, there we go, right?
Yep, I see it now.
In C++, right? Well, C++ is getting complicated because there's many versions now, and C++ 20 was just finalized, I think, last week or the week before. And that's an entirely different thing. But in general, right, we don't have garbage collection in C++. And so when you're done with an object, you have to make sure you delete it. And usually you want the object or the method that created that object to actually delete it. And the problem here is there's no way, if this was C++, the list of students would have created that object, but it's been released from that object, and so there's no way for that object to know when to delete it. So you have to be careful with that. But that's, if you deal with C++, then you're used to having to constantly worry about memory. And if you deal with C++, you know what I'm talking about. And if you don't, then you have no idea. I mean, it's an entirely different beast than, say, Java or Python. Another issue is who's in control of the iteration. Given an external iterator, or some people call them active, the collection is not involved in going through controlling iteration, right? We do it externally. So I ask for numbers for the iterator, and here's a code that's responsible for going through and controlling the iteration. Now I'll go next, I'll do some other stuff, and I'll come back to you, now I'll give me another one, right? So the client code actually is the one in charge of controlling when and where we go. It's an extra element. If we have an internal iterator, we basically say, we call a method on the collection, we pass in some sort of lambda that the method will use, and then that method will go through all the elements, right? So in an internal iterator, right, the iteration is controlled by the collection or by the method we called. Now this, there are several advantages for internal iterators. One is they tend to be easier to implement. You know, if we have an iterator over a list, it's not too hard. But think of a tree structure, right? I've got to have some sort of n-ary tree. And I want to go through all the elements of the tree. The problem is there's no clear next, right? Because you start at the root and then you go left and then you have to go back up and right. And so you have to keep track of where you are and where you've been in the tree, iterate through. And that becomes somewhat complicated when you have an external iterator, but internally it's much easier. The second big advantage of internal iterator is we can now parallelize this iterator. Because the method find all is in control of what to do. So if you look at things like a Spark, Spark uses basically internal iterators for most operations you perform, and that allows them to take the data, separate out pieces, and then do run that iterator on multiple blocks of data in different machines, and then bring the answer all back. Another issue is who defines how the reversal goes. Again, if you get an array, it's pretty easy. You keep a point of where you are, and then you just go next, right? But if you have a graph structure or a tree structure, then how to go to the next element becomes more complicated. So here the issue is, say you have a collection, in this case a vector. I think it's the iterator for that vector or that collection, and then I change the collection. I delete an element and add an element. What happens then when I ask for the next element? What can happen? What should happen? Let's say I have a list. Let's say 1, 3, 7, 9, and let's say some sort of list like this. And now I better add another element, 12. And let's say my iterator is currently located at 3. And what happens now if I delete 7? And I ask for the next element, should I get to 7 or should I get to 9?
The 9, ideally.
What happens if I delete the 3? What should be next?
A null value.
But there's more elements of the list.
Actually, would it return 1 then?
Should check the next element already in the.
Say that again.
Should it check for the next element? If there is a next element, shouldn't it start pointing to that element?
Yeah, it should check, but if I delete the 3, right, and it was pointing at the second element, right, and I say next, I should get the third element, right? So should I get to 7 or should I get to 9?
Should be 7.
7.
But the 7 now was the second element, not the third element.
Doesn't seem like it'd be deterministic.
Right, and that's a problem. There are situations where it's not deterministic. And if it's not deterministic, that's a problem, right? We don't want our code to act randomly. And what happens if I'm at the 3 and now I add a 2 in the middle, right? Do I go back to get the 2 or not? So when they talk about robustness of the iterator, they're talking about how well can the iterator handle changes on the list while you're iterating over through it. Luis?
It's probably not good programming practice to change the object of the iteration during the iteration.
Right, and so what Java does is if you change the list, the collection you're iterating over, while you're iterating over it, when I call has next, an exception is raised.
Uh-huh.
So a lot of languages have that policy where if you make a change, then next time you try and call that iterator, you'll get an exception saying, look, I mean, there's all kinds of policies one can use. One could say, well, when you create the iterator, you'll iterate over the original collection, and if you make a change to the collection, iterator retains a copy of the original collection. But you want to make sure that whatever happens is deterministic and makes sense to the people using it. So most iterators now just say, well, you changed it. I'm going to raise an exception so you know that something's happened. Now, one question you can think about is, how does Java know that you've actually changed the list when you call has next?
It can't be checking sameness at every step, can it?
What do you mean by sameness?
Meaning it stores a local copy and then compares the list at every next to the local copy?
That would be expensive both in memory and in.
Yeah, that's what I was thinking. Too expensive.
What if there's 100,000 items in that list, right? So what Java does is, for each time you make any change to a list, it keeps track of the number of changes that have been made. When you add an element, you delete an element, move any sort of change of location, those are indicated as a change. And so when an iterator is created on a collection, the iterator keeps, stores how many changes were made to that collection when the iterator was created. And so hasNext always checks its number of changes that were made versus the current number in the collection. If they're not the same, then we'll raise an exception. That means every time you add an element to an array list in Java, not only are you adding an element, you're also incrementing that counter. Okay, any questions?
Is that counter allocated when you create a list?
Yes.
That's okay.
A related topic, because this is becoming pretty common these days, related to iterators. Iterators are a way of going through a set of elements in a collection. And Java streams also allow us to do operations on elements of a collection, right? And so a stream is just like a sequence of values, and we're now going to operate on those values, and we can then chain them together. So for example, say I have created, an array of words, convert it to an array list. I can then get a stream out of it. Now I can filter them, which what this does is going to select all the words in that list with a length that's greater than 2. Then I'm going to, from that resulting list, I'm going to only select all the words that start with A. And then all the words that are greater than length of 2 and start with A, I'm going to then change into uppercase. And then I'm going to collect all the results and set them to long words. Is it clear what's going on here? And again, I would say, here's another example where lambdas help the code to be a bit more readable to understand the intent. The two filters, filter means I'm going to select things that satisfy a condition. There's a condition. I'm not worried about, for I equals 0, I less than length of this collection, grab the element out, check it, just filter means you're going to select the ones that satisfy this condition, and all those details of selecting the items are done for us. All right, and then we can print it out. The other thing you note is that the streams are smart enough and the compiler is smart enough now that we're not making 3 separate passes over the list. We don't go through the entire list and then filter out things that are greater than 2 and then go through that list. We'll start with A and then go it again. We basically make only one pass over the list.
Anyway.
Right. And again, this is this type of operation is becoming quite common these days. Any questions? No. Another example, right? So in Java, right, there's, here are the different types of methods we've got. Filter, find first, for each, find the min, find the max.
Oh, yeah. Oh.
That's.
Oof. Oh.
Okay. And of course, different languages have different set of iterators. I don't know any Ruby programmers out here, but here's some Ruby iterators. Python does have filter, map. And these are sort of the big ones that You know, what can I say? You know, years ago, Google published this paper on MapReduce, showing how they were able to do searches so fast. They were able to parallelize them on multiple machines. And from all that came Hadoop, which used map and reduce. And then Spark came a little later, and they expanded upon these. But these are very, very common functional languages, even though per se they're not, nothing special about these functions. They first came out of Lisp, you know, many decades ago. Smalltalk had them starting in the 70s. And you should get familiar with these functions, because they're very useful. Right. So reduce, I'm going to find elements. Well, it's just reduce initial element 0 plus, and that will do it for us. I want to find product, right? That's all we have to do. You know, using reduce, concatenate all the strings in a collection. Finding the max. You know, filter, what is what it says, right? I'm going to give a condition, and I'm going to select all elements that satisfy that condition. You know, find all things which are greater than 3. All right. And then we're going to sum them up. The map just transforms all the elements in a collection, returns a new collection. So here I'm just adding 5 to all the elements of the collection. And here I'm taking a dictionary and just returning all the values of the keys. Right. So I'm taking a list of numbers, I'm scoring them, and then summing them up. And just to give an example of something you do with these functions. You know, these days, you know, I avoid using the standard for loop, and I try and use one of these functions to accomplish my task, in part because it's shorter and it shows the intent of what I'm trying to do better than going through this crazy for loop. So that's iterators. Any questions? No questions. Then I want to start looking at 2 other patterns. One from the text and one is not. And the decorator pattern is illustrated here. I assume most of you, or some of you, have seen these dolls. The same doll nesting each other, and they take top off biggest one, and the smaller doll inside, take that out and take it apart, and you keep on going and take it down to the smallest one inside. The intent of the decorator pattern is to add responsibilities to individual objects dynamically and transparently. By dynamically, they mean at runtime. So at runtime, I can add more functionality or change the functionality of a particular object. I'm not modifying its class, adding methods to the class, I'm adding methods to a particular object. And by transparently, what they mean is, right, your code can't tell the difference between what it was before or what it was after you've actually modified it at runtime. So the structure, first of all, we need a interface or an abstract class, depending on what language you use and what construct is available. It defines the interface, all the operations you can perform on the actual object. And then we've got the concrete components, and that actually implements various operations. The structure only shows one operation, but there could be many. And then the decorator, again, there's an interface and it has a property or a field or a data member which holds a reference to the component. And then you have multiple different decorators, concrete decorators. That's the structure, but it doesn't tell us how it operates. So at runtime, right, so here's our actual component or object. And here I've got two decorators around it. And the decorator, you know, the client now interacts with the outmost decorator and call a method on it. And that method will be sent to the decorators to the actual component. So I stole the example from Wikipedia, and it's a public source, so I feel fine in doing that. So the example is to explain how the decorator works is, you know, we're selling coffee, and you know the coffee has base price of $1, but there are various options we can choose, right? We can add milk to it, we can add sprinkles, right? So the different costs. So, you know, one way we can do that is we can have an if statement saying, well, if, right, if you've got milk, add this, if you've got sprinkles, add this. And for each different type of add-on to your coffee, we have to add an interface, we have to add an if else inside someplace in the coffee object. Using a decorator pattern, you know, here's our top interface. We've got two methods, give me the cost and give me the ingredients. If you just have coffee, then that's easy, right? The cost is $1 and ingredients is just coffee. Pretty straightforward so far. Now for decorator, you know, here's our decorator. It has a coffee in reference to coffee. Right, and then we can give it a coffee object, which it decorates. And then we have two methods, right? We need be able to get the cost, get the ingredients. Still haven't done much yet. The fun part becomes on the next slide. So now I can create a with milk class. And now the cost is whatever the base cost is, whatever that is, plus for milk, right? And get ingredients, right, is whatever ingredients are passed to us, plus milk. So now when someone orders just coffee, we can instantiate a simple coffee object, and that will tell us, okay, the cost is $1, ingredients is milk. If you also want to add milk, then we decorate it with milk object, and that will then help automatically compute the cost and add milk to the ingredients. So far, so good. Right, so now we can do things like this, right? So my print info is going to print out the cost and the ingredients. If I just want straight coffee and I print out the info, the cost is going to be $1 and the ingredients will be milk. If the customer wants to add milk, right, we then instantiate a with milk object, pass in the coffee object. And now when I say print info, the cost is going to be $1.50. And the ingredients is going to be coffee plus milk. If you also add sprinkles, right? And now when I print info, the cost is going to be $1. I forget what sprinkles were 20 cents. So $1.70 plus ingredients will be coffee, milk, and sprinkles. So at runtime, depending on what the customer orders, we can decorate with milk or not, or with sprinkles or not. And if we want to add more options, we don't have to go inside the coffee class to change the if statement inside. We just say, okay, we create another decorator, and then at runtime, we put together the order, we just compose the coffee object inside, put inside another decorator, Right? And so then we get, using decorators, we can extend the functionality or how the main class works. Is that clear? If we knew in advance that there's only going to be milk and sprinkles as options, it would be easier to have a case statement inside the coffee class and have the coffee class keep track of whether you got sprinkles or not, and then you compute the cost. But when we do that, we're deciding at compile time what options are available, and to add more options require us to go back and recompile that class with a decorator now, right? At runtime, we can decide what options to give. And if we want to add more options in the future, we can just add another subclass of decorator. So it does give us more flexibility. And this, examples like this are always fake and they're always very simplistic. So one place I know where decorators are used to make code simpler, in Visual Smalltalk, their windowing environment, some windows are just windows, right? But sometimes you want to be able to scroll vertically. Sometimes you want to scroll horizontally. Sometimes you want to do both. And keeping track of where you are, when you can scroll vertically and horizontally or not, becomes somewhat complicated. So what they did is their basic window object or class did not handle scrolling at all. They made it much simpler to implement that class. They didn't have to worry about scrolling at all. And they then used decorators. They had a vertical scroll decorator and horizontal scroll decorator. And those decorators then were smart enough to be able to modify the window that is displayed. So it became much easier to implement because the base window class, no scrolling, don't worry about it at all, just put things up in the window. The vertical scroll decorator only had to worry about scrolling up and down, right? That was it. And the horizontal one, same thing. Hart, you got a question?
Yeah. So, I don't think these decorators would work together to create a vertical and horizontal, would they? You'd have to create a new decorator called horizontal and vertical. Is that
No.
correct? Okay, they could work together.
They work together, so you would when you wanted just a vertical one, you use a vertical decorator. On both, you had two decorators on the window.
Okay, so you do extends vertical decorator and extends horizontal decorator.
Yeah, basically you'd have two decorators on the base window. Yeah, so some examples. So yeah, this example, right? The coffee example is completely fake. It doesn't deal with price changes, new extras. There's always seasonal extras, right? I mean, you get at Thanksgiving time, you get various Thanksgiving related coffee. And so we really need that system to be driven by data, right? There has to be some data besides here's the price, here are the current options. And these days, right, well, used to be in the cash register, the clerk just entered the amount each item. These days, the cash register has a list of all items you can purchase at the store, and they just press, they bought, that type of coffee with this feature, you just press each button. So in reality, that example is completely fake, because you really have to deal with all these other issues, which make it far more challenging system to implement. Now, since functional programming is becoming more common, once in a while I'll take a look at these patterns and say, how do we do this in functional programming? And the answer is we just compose functions, right? And so you would have a a base price function with milk function with sprinkles, and then with milk function would take its argument and add 0.5 to it. And sprinkles would take its argument and add 0.2 to it. And there's various ways you can deal with it. You would just compose functions. And most functional languages have a way of chaining things, so you can actually read it better. So this is a closure. You start the amount, get it through base price, then with milk, with sprinkles, view tax. And again, I just several comments multiple times is that map and reduce and chaining functions becomes quite common in functional programming, and it's always interesting to know how these object patterns map over to functional programming and vice versa. Right, so basically, yeah. And of course, you wouldn't really do that. You'd probably use maps. As I said early on, right, or last time, when we looked at the two design principles, one was favor of composition over inheritance. The decorator's example of that, we're going to compose objects rather than create a subclass for a window type and a horizontal scrolling window and a vertical scrolling window, and then a subtype for both of them. That would be inheritance, but the decorator, we're using composition. We have a base window and a decorator which does vertical scrolling and a decorator which is horizontal scrolling, and then we can compose them to get what we want. A plain window, vertical scrolling, horizontal scrolling, or both types of scrolling. So it's an example of us pattern using this design. So yeah, benefits, like I said, in the window case, it greatly simplified the window because the base window, you have to worry about all the complications in scrolling and keeping track of where you are. And it also separates out, the fundamental issues of that class versus embellishments. Yeah, and there are some liabilities. The first one, change of identity. To make the pattern work right, we always have to refer to that object not as its concrete type, but as a type of its parent abstract class. In the window example, it wasn't just vertical scrolling, horizontal scrolling. They had lots and lots of decorators. And so when something went wrong when you're building an interface, it wasn't that you had one or two decorators, you had 10 or 15 decorators, and it did make it hard to deal with trying to understand when something wasn't going right, where in the decorator chain was the problem. And the third one is the two examples I gave, right? It seemed obvious that we could compose them any way we want, but there may be decorators where that will not be the case, right? And then you have this problem of making sure that we don't combine two decorators that don't work together. And that can be hard because if there's decorator A and B can't work together, A could be over here and then a bunch of other decorators, and then we put B, and how do we know that there's an A in this chain? So far, so good. Yeah, I will. 5 minutes. I will just start this today and then we'll come back to it. The null object pattern, we create a class that represents nothing. So again, the structure is we have this abstract class or object, and the real thing has to implement that interface, and so does the null object. And then the pattern says do nothing. And it's maybe more appropriate to say not do nothing, but does the correct thing for nothing. My favorite example is a link, linked list. And there's always special cases. What happens when this is empty? And then when you add an element, right, we have to always check, find, what, we're always checking to see if there's a next element. So we get special cases. So we can use two different types of null objects, one for the head node and one for the tail node. And now if we want to print these out, print the list out, what can we do? Well, I can ask the head node to give me my string. The head node, it's just a null node, so doesn't contain elements. So it can return the left paren and then ask the next element to give me the rest of the string. A regular node just gives its element and then whatever it returns next. And we never have to worry about it being at the end because it's a regular node. And then a tail node, it knows it's at the end, and so we just return, right, the right paren. And so one way to deal with the special cases is to have two different types of null nodes, one for the head node and one for the tail node. In this case, I want to print things out. It's just each node is going to do something different depending upon what it is. Regular nodes are just going to give me my element, and the head node will give me the start of the list, and the tail node will end it. And next week we will start with a null node pattern or null object pattern. And next Tuesday you'll have your assignments back, and we'll talk about that too. Any last minute question, issues? Okay, I will see people on Tuesday then.
Thank you.
Thank you.
Have a good night.
Thanks.
Thanks a lot.
Thank you.